Okay. So graphs of some common logarithms. Oh, where do I want to get down? So let's take a look at example 1. So we kind of graphed the inverse of an exponential function in that last section, right? Remember that, the very first one? And it was the reflection in line y equals x. So let's take a look at this function. Y equals log, whoopsie daisy, always does that, log base 10 of x. So we're going to graph that. So we're going to want like a table of values, right? So let's get our calculator and see if we can make a table of values for this.
I still can't get the calculator to work.
You still can't, huh? Jeez. Are you ever at the school?
My dad's.
All right. So let's see if we can get a table of values here real quick. Log base 10 of x. So you really didn't need to write the 10, did they? So let's bring up our calculator. Down here. And so let's find some points we can plot. So, all right. So if you recall, we want to go over here to functions. Okay. And then go down to add a, whoops, it was already on it, add a function. Okay. And so down here, it's hard to see. You see these two buttons here? So this one here is a natural log. We'll get to that a little bit later. And this is our log base 10, the common log. Okay. So this calculator only does base 10. So we're going to do log, and we're assuming it's base 10, right? Of x. Hit OK. So let's go up then to table. Well, let's take a see what the graph looks like. Does that look a little like the graph we had in the previous section?
Yeah.
So that's the graph of a logarithmic function, right? Which is the inverse, right, of your exponential graph. Let's go up to table though. Oops, I'm going to get back. And like upward, forward. There we go. Okay. So do you notice? I want to set this interval here. Here's what I want to do. I want to see some other values in here. So I'm going to go over here to set the interval. I think that'll work. Oops, no. Hit this button and go up, down to that. Okay. So let me have the x start be like at, I don't know, let's call it -1. See what happens. And then we'll go out to x of 10. But here, I want to do this step, instead of counting by ones, maybe I want to go by 0.1 for each value. So go ahead and set your calculators like that if you're doing this with me. You should try to do this with me so you can do it on your homework, right? And then hit confirm. Okay. So notice we have a bunch of values here that are undefined. We'll address that in a minute. Let's go down and see if we can find some points. Oh, that's right. I gotta get this. Keep this. Right? So look at all these negative values that are undefined. And here's our first value. At x of 0.1, y equals -1. Right? So let's plot that real quick. So 0.1, like 1/10, right? So if we go back to here, let's put some intervals in here. Let's go 0 to 10. So halfway would be about 5, right? And then 1, 2, 3, 4, 5, way off. 5, 6, 7, 8, 9, 10. Okay. Not exactly the scale, right? And this would be, so that's 2 and 2. So this is -1, and that would be 1. Everybody agree? So he said at 0.1, we had a value of what from the calculator? -1, right? So at 0.1, we have a value of -1. So right in like here, okay? Well, let's see if we can find any other maybe integer values that we can plot, okay? Let's go back to our table, all right? Let's scroll down. We got a bunch of these decimals here. Let's see what we have. Okay, there's a nice one. At x of 1, we have a 0. Let's go put these guys in here. There's that. So when x is 1, we are at 0. So there's another point. And let's see if we can find another integer. It would be handy. See any more in here? 2, doesn't have 1. Too many more here. Well, maybe we're going to have to plot some of these guys in here. I don't see any more. Let's go back up here. And you can hear me tapping on the screen, right? What's an x of 2? 0.3, we can probably plot that, right? So for 2, we're up at about 0.3, about a third of the way up, right? And let's go down to 3, about 0.5, right? 3 comma 0.47 or 0.5. So here's 3.5 like that, roughly. Okay, and we can keep going back and forth to the table, right? And then 4 would be like up here, right? All the way out to 10 would be at 1, right? So our graph, and this is a real kind of a mess, should look like this. Okay? Yes, I know I missed some of the points completely there. Hopefully you can do a little better job with yours. It's a little tough on this screen here. Okay? But notice as you move to the left on that graph, are there any negative x values that are valid?
No.
No, right? So if we talk about our domain, and the domain is all the values of x we could possibly have, right? It would be all x such that the x's are what? Always positive, you'd agree, right? Always positive? So how do we write that? All x such that x is what?
X is more than 0.
Greater than 0, right? All right, so your x's for this function will always be positive. Now, what about the range? Are there any limitations on y?
X y then y at 0 less than 1
Well,
or equal.
if I look over here, I've got y values greater than 1, right? This keeps climbing, doesn't it? To the right. And look what it does going to the left. So wouldn't you agree that y would go from negative infinity to positive infinity? Right?
Yeah.
So we'd say all y such that, well, we could say any real y value. So we could say that, remember, y is any element of the real numbers, right? From negative infinity, remember that symbol? Y is an element of the real numbers. That makes sense? Or if you wanted to do it in interval notation, right, you could do this, negative infinity to positive infinity, right? Either one of those. Okay? All right, let's think about though, right? So think about this graph as the one we did on page 61, right? Does it look a lot like the graph on page 61 that we started with the inverse of the exponential?
Yes.
Okay, so keep that in your brain. Let's think about why, or how come, x in this function here can never be negative, right? So what does that mean? Log base 10 of x. Let's think, why can it ever be 0?
No.
Let's think about this. If log base 10 of 0, right, equals something, right? Doesn't that imply from what we did in the previous section that 10 to some power equals 0? Is that possible? Can you write?
No. Because x 10 of 0 would equal 1.
Correct. There's no way to do an exponent and have a 0, the result be 0, unless the base is 0, right? Okay?
As well as the fact that all negative numbers would just be 1 over.
So an x of 0 was undefined, exactly right, okay? And also because 10, so 10 to the x, right? Well, let's just be even more general, right? Not even, we don't have to use 10, right? Any b to the x cannot equal 0 or, as you said, be negative. Because there's no exponents that will cause a negative result, right? So that means we have what's called an asymptote line here. It will approach this line, right? That x equals 0 line, but never cross it. Does that make a little sense to you? Okay. Does anybody have any questions on this first example? Like maybe like to get the table of values, right? Plot some points. You don't need a whole ton of them. You know kind of what the log graph will look like now, right? So you just need a few points to, locate it properly. All right. All right. So before we get to this next function here, if you're using this online calculator, remember it only has base of 10 or natural log base e. Let me give you a quick note. So that even if your calculator only does base 10 logarithms, there is what's called a change of base formula. So you see this one here has base 3, and your calculator won't do base 3. Some will, but there's a way to do that, write an equivalent of that. So let's go to our notes page real quick, and I'll show you how to do that on your calculator. Okay. So this would be our log change of base formula. If your calculator does any base, you're fine. Okay? So if I want to put in my calculator the log of some base b, any base, right, of any number, I can, if my calculator doesn't do base 3, whatever it is, I can rewrite this expression here as the log base 10 of a, right? I'll put a 10 in there even though we don't have to write it, divided by the log base 10 of b. And that your calculator will do. And normally you don't write the 10, but I want to be clear here. Now also, this will work as well. You can use we'll get to natural log later, ln, right? You could write it as natural log of a over the natural log of b. I know you don't know what that is yet, but okay. But this is what you can enter into your calculator to get the equivalent graph or a table of values or something as this thing, whatever the base is, if it's not base 10, okay? So keep that handy. If you're using this online calculator we have, you probably have to change the base every now and then. Does Desmos do log of any base? Rourke, you said you were using that, you know? Anyway, everybody have that? Let's go back. Okay, down to exercise 2. All right, so we have a function log base 3 of 2 minus x. Okay, we're going to use a table again. We're going to use a table, but we're probably going to have to use change of base. Unless your calculator can do base 3. So it's not base 10. So let's get a table of values to graph this thing. So let's go to our calculator, and it's log base 3. So what would this be as change of base? So let's take this and use that change of base formula. Log of what? Based on that formula I gave you.
Log of solid
2 minus x
2
over
minus 1 over log of 2 of 3
the base, right?
of log 10 of 3.
Yeah, and those are both base 10, right? So that function they gave you and this one I gave you with the change of base, they are equivalent, okay? They will give you the exact same graph and the exact same table of values. But just the one I gave you now uses log 10 if your calculator only does log 10, base 10, okay? So let's go to our calculator then. See what we got here. So I want to hit my little back button from here, I think, and then go to over here to functions. Let's clear that one out of there and replace it with that thing that I wrote. Now we got to be careful with parentheses and whatnot, I think here. So we want to type in log of 2 minus x, right? 2 minus x. Let's get outside our parentheses and hit divided by, okay? Log of what? 3. That's what it gave you, right? Is it okay? Let's see what the graph looks like here, right? On the plot graph. Well, that's a little bit different, right? Probably because of that negative x in there. Let's get a table of values. And looking at this graph, right, I probably want a table of values from, oh gosh, I don't know, a graph on a page, like from -10 out to what, 2? All right, so let's hit this button and go over here to table. I'm going to hit this back button, go down to set interval. Okay. Okay. The graph's going the other way, so I'm thinking maybe -10. Let's go out to 3 just so we can see some undefined stuff. 3, and maybe we'll do 0.1 like that. Hit confirm. Okay. So here are some values. Maybe I could split screen this. That might work. Oh, it's not big enough though. Maybe this. Okay. This might work. Okay, so we have some values over here. I don't, let me do this. Darn it. I thought that was one. Still want to go to touch it. All right, so at -10, right, we're at about what? 2.26. So -10, 1, 2, a little bit over 2, like that. And then let's take our. I gotta get enough room to do my calculator screen. Oops. That. Let's make that bigger. Okay. So -10, 2. Let's get some other values here. How about, I don't know. See if we have any integer values. One up here. Oh, -7 is it 2? It's an easy one, right? So go over here to -7. Get dot there. 987, and that's at 2. Okay, so let's go down, find some more stuff on our calculator. It's -5. Let's do -5. Is it 1.7 something? 5, right? About here, like that. Any other useful values here? -2 is at about 1.2. So -2 about here. Let's get a few more. Ooh, -1 is at 1. We got that point. Nice. Oh, I thought that went to, that wasn't enough there. Let me go to the table set. Oh, darn it. I thought I set that interval correctly. -10 to 3. Why wouldn't it go? Give me a second. Why is it not going to 3? Well, anyway. I know what they are. So I think we have 1, 0, right? And then it keeps going down like this, right? So this is going to be our graph. Okay. It's kind of tricky to do, get that calculator to split screen with this thing. All right, so does anybody see what the asymptote line would be here?
Asymptote line would be 3.
X equals what?
X equals 2.
So this is X equals 2 is our asymptote line, right? Why will X never be 2?
Because of the exponential function of 2 minus x, we're doing the 2 equals the asymptote line.
Right? And we cannot take the log of 0 or anything less than that, right? And it can't be negative. Does that make sense? So that's where that asymptote line will be. All right, so let's write down here the domain, the x values. So our domain will be all x such that x is what in this case? More than 2 or less than 2?
Would be more than 0, more than 2.
So out here?
No, less than 2.
Yeah, be careful, right? So x will be less than 2. Okay? Because if we plug anything 2 or above up into this function, we end up taking a log of 0 or some negative number, and we know we can't do that. Okay? Let's take a look at the next example. So we have another one here, log base 2 of x plus 3 and then minus 5. Okay? So a table of values, I'm not going to fumble around with that anymore. Can anybody tell me where the asymptote line would lie?
The asymptote line lie in
What value of x would stop making sense for this
x
function?
of the sword.
X of negative 3, right?
Negative 3, yeah.
Because what's negative 3 plus 3?
0.
0, right? So we know we have an asymptote line. Let's go to x of negative 3 and put that in here. Right? So x equals negative 3. That's our asymptote line, right? It's asymptotic, as they say. So let's get some values here. I know that we have like, if we did the table, negative 2, I can't see, 1, 2, 2, 1, 2, 4, somewhere down in there, right? And then negative 1 is at 1, 2, 3, 4, there, like this, somewhere in there. And then 0 ends up like here, oh, and 1 is like here, roughly. It kind of goes out like this. And that's 1, 2, 3, 4, 5, negative 2, 1, 2, 5. So we got another point like here. So this is assuming that we did a table of values, right? And that's what that graph would look like. I just don't want to take the time and monkey around with that calculator again. It's a lot of time. Okay? So that looks like an inverse of an exponential again, right? But notice what do you think this negative 5 does to the graph?
It times it.
No, that's subtracting. If you're thinking of making a
subtracting,
table of values and you subtract 5 from all the values, it shifts the graph which way?
Down 5.
Down. So it's like a translation from geometry, remember? You guys that took geometry, down 5. Now adding 3 is actually opposite of what you think. It actually shifts the graph to the left 3. Okay? So that's why we have, instead of an asymptote of 0, we have an asymptote of -3, right? So let's think about the end behavior. Remember how this goes? So down here, describe the behavior. So let's think about as x approaches -3, right? As x approaches -3, like in that direction, what happens to y? What does it approach?
Y decreases.
How
Or
far?
decay.
What does it approach?
It approaches the
Remember this notation, as x approaches -3. Look at the graph. What does y approach? What value?
Y approaches negative infinity.
Negative infinity, right? It keeps going down. Okay? What about as x approaches positive infinity? Going the other way, going to the right now. As x approaches positive infinity, what does y do?
Y approaches 3.
No, we're going to the right.
Yeah.
As x approaches positive infinity, what is y approaching? The graph, what is it doing?
It's approaching
Positive
Positive
infinity. It keeps going very slowly, right? But it still keeps going up. Okay? All right, any questions on that exercise? All right, a couple more down here. We'll put a bow on this. So let's think about the domain of this function here. The domain, right? So we have to think about the asymptote line. Like, what can you not take the logarithm of, right? So it's a log base 2 of 3x minus 4. So that means that what's in that parentheses can never equal what? What can you not take the log of?
You cannot log the x.
You cannot take the log of 0 or
0 or a
negative numbers, right? So whatever is in here has to be greater than 0, right? Positive. So the way you find the domain here, right? So we just to reiterate, we cannot take log of 0 or negative numbers. So cannot
Actually, accept those notation.
of 0 or negatives. Okay. So let's see what value of x would cause that to be 0 or negative. So let's do this. Let's set it greater than 0, right? Because you know it can't be 0 and it has to be positive. Everybody with me on that? So now we can find the limitations on x. If that thing has to be positive and not 0. So add 4 to both sides, you get 3x is greater than 4. So x has to be greater than what?
It has to be greater than 4/3.
4/3, right? 1/3. So in set builder notation, this would be all x such that, well, quite simply, x is greater than 4/3. Okay? Because an x of 4/3 will cause that thing in the parentheses to hit 0. That make sense? Okay. All right, let's go down to this last example here, right? Let's talk about the rate of change. Take a look at the graph up here, right? So you notice how our graph here, as we go to the right, this one starts to climb very quickly, and then it climbs more and more slowly as you go along, but it's still increasing, right? And between any 2 points, we can do an average rate of change. Remember how to do that? Right? Average rate of change. That was just like y2 minus y1 over x2 minus x1. It's like slope, isn't it? Okay. So here's our function with the common log. Okay. F of x equals the log of x. Okay. So that's our function. What's the base of that function?
A should be 10.
10, right? So we need to find f of 10 because they want to do the average rate of change from 1 to 10, right? So we need to find f of 10, right? So it would be the log base 10 of 10, right? What's the log base 10 of 10 equal to?
10 would be 1.
1, right? Just 10 to the first equals itself, okay? And what about f of 1? That'd be the log, oh gee, of 1.
10.
Well,
That'd
10,
be 1.
10 to what power gives you 1?
So,
10
Zero.
here, 10 to the 0, so
Yeah.
that equals 0, right? Okay, so now we just do our change of base. Or change of base, good grief. Average rate of change, let's try that one. So we have to do 1 minus 0, right? Over 10 minus 1, right? Remember doing this? So that's 1 over 9. And if you put that into decimal, it'd be approximately 0.11. Okay? So it has an average rate of change between that interval, right? From 1 to 10 of 0.11 or 1/9. Right? Let's try it for the next interval here. Now let's see what the average rate of change is between 1 and 100 instead of 1 and 10. So we need to find f of 100, right? Which is the log base 10 of 100, which is what?
10 to the second, or 2.
Just 2, right? And then f of 1, again, we already know from up above, right? We didn't know that's 0, isn't it? Okay. Now we just do 2 minus 0 over 100 minus 1, right? So 2 minus 0 over 100 minus 1. So that's 2 over 99. Seems like a little smaller number, doesn't it? But as a decimal, it'd be approximately 0.02. So do you see how as you move along, the rate of change starts decreasing and decreasing? Okay. So what can we say about that? As x increases,
Y.
no. What happens to the average rate of change between here and here, these two numbers? F of x climbs how? So look at from 1 to 10, it's got a rate of change of 0.11. But then from between 1 and 100, it's got a rate of change of 0.02. So is it climbing more quickly or more slowly as you move?
Slowly.
Yes, it climbs more slowly. But it still keeps climbing to a y of infinity. Okay? All right, I know that was a lot. It took a little longer than I thought, I guess. But does anybody have any questions on this? Okay.